for next week. I will send an email asking you questions with regard to, are you interested in analyzing real data? Do you want to take quizzes and get added to ICON? I'll send that email out this weekend. So if you don't get it on Sunday, that means you didn't make my email list. So if you don't get an email by Sunday, go ahead and send me an email and I will add you to the list and make sure you get all future emails as well as that one. So today we're going to finish talking about the topological persistence and simplification paper. This is the older method, which is very visual. And so we will finish up that method where for both methods, we have a filtered complex, so just an increasing sequence where this one embeds inside of here, etc. And then we got this nice visual representation of the persistent homology. We're going to go ahead and focus, so just to remind us again of some terminology, we do have positive simplices if they are a generator, if they create a cycle. All vertices are cycles, so every single vertex will be a positive simplex. But then we can also have negative simplices, and those become our generators. Those are the things that destroy a cycle. So we had 3 cycles over here, but then when we added this edge, we now only have 2 cycles once we mod out by the boundary. So we still actually have the 3 cycles, but when we mod out by the boundary, we say S and T are now equivalent. And so plus corresponds to generators, cycles. So we can have our 0-dimensional cycles, our vertices, our 1-dimensional cycles, our circles. So those are positive, as well as our 2-dimensional cycles. This actually, once I add in STW, we form a 3-sphere, well, topologically equivalent to a 2-sphere. So this is actually the boundary of a ball, just one that looks a little bit more polyhedral than round. So our positive simplices are our generators. They're the creators of our generators. And then we have the negative simplices when we go ahead. So here we've got a nice negative simplex where we now kill this cycle. So we kill this generator, so it becomes a relator. And remember, we wanted to pair our relators with our generators so that we could easily cancel them out. And we talked a little bit about that last time, but it was such a simple case we didn't see the full case. So now we're going to go ahead and focus specifically on this part of the diagram, because that's the more interesting case. So we'll leave it as homework for you to do the other pairing for the beginnings part, actually all the way up to here. The things that I'm going to pair are the negative 2-dimensional simplices, and we will pair those with the 1-dimensional edges that are generators, not relators. So we're pairing with the negative 2-dimensional ones with the positive ones here. So let's zoom in on that. So I still have a little bit of my triangle down here. So thus you can kind of see that all of these vertical lines, those corresponded to our generators, our positive simplices. So we've got our positive simplices are all these. So those are our positive 1-dimensional simplices. And we wanted to pair them with these, with our dotted hypotenuses connecting them. These right here are all, I guess let me put pluses so that we know that these things are all plus underneath there. And then I'll use underlining of the 2-dimensional ones to note that they are negative simplices, and thus we want to pair these negative ones with these positive ones. So we've got these generators, 7, 10, 11, and 12 are generators, 8 and 9 aren't, and you can see in the picture above, 8 and 9 were both negative. And we want to pair these things here. Well, let's start first off with the TUW. I'm going to redraw TUW. So we're going to redraw this way here. So I'm modifying my picture a little bit, so we're sort of like punching it out a bit. flattening it. So we've got our T, our U, and our W. So when we add this space, we've now just killed a cycle, so I need to pair it with something. Well, we go backwards in time and we pair it with the youngest. TW was born at time 7, TU was born at time 12, so I want to pair it with the one that was born later, the youngest. And so you will go back here and pair it with this one. So 12 will be paired with 13. And I will also notice the ones that it could have been paired with. It could have been paired with TU, so I will put TU down here as well. So we can pair, so since this thing here cancels out this one cycle, that one cycle is created by TU, UW, and WT. So it will also be paired with UW, as well as TW. So I just put the entire boundary, as long as they're positive. Since the entire boundary, these are all positive simplices, we go ahead and pair it with all of those. But the main pairing is 13 is paired with 12. So when we do the modding out by, we will cancel out 12 using 13 instead of 11 or 7. So now we need to go ahead and go to SUW. So SUW, I already have U and W drawn, so I just need my S. And we now want to add this thing right here. Well, I added TU. So TU, I kind of want to just sort of note, I'm going to put a dot here, that we've already taken this as the generator. When I now go back to SUW, well, I can choose SU, SW, or UW as long as they are positive. So I just go back until, well, TU is not part of that boundary. Then I can go back to UW, that is part of the boundary. And so we will pair 14 with 11, so we'll add a 14 here. And then we will note that the boundary of SUW is UW, as well as SU, as well as SW. However, the fact that my SW is not very readable doesn't matter because SW is negative, it's not a generator, so I really shouldn't have listed it. I only want to cancel out potential generators. The generator I'm going to cancel out is UW, but it's nice to know that SU would have been another possibility. So, but we chose UW, and so now we're going to go ahead and say we've got this thing here as well. The next thing we'll take a look at is STU. So now I just need to add in the edge ST, and we're now talking about this triangle here, the STU triangle. So I want to go ahead and pair it, so I will go back. TU is a possibility, but TU has already been paired, so I can't take TU. And the question is, well, what do I want to go back to? I actually want to now add two things. Let me see if I can change my pen color to something else now. Yeah, I was working with STU, but now I'm going to add in the additional triangle. Since the edge TW was already taken, I'm going to add in these things right here, and now work with the boundary of this one instead. So I want to work with the youngest cancellation, and if I work with the youngest cancellation for this triangle here, I would have been getting TU, but TU's already been taken. So I don't actually want to work with this cycle. I instead want to work with this cycle so I can still do the youngest calculation, cancellation, which could be TW. So what we do here is add on the boundary. So the boundary of STU is ST plus SU
as well as TU. And I will join that together with my TW. So everything here, I will join it together with all of those. So I've got my TW, my UW, and my TU. But I didn't want TU. Well, the way to get rid of TU is if I add this triangle together with this triangle. Well, we're working mod 2, so the TU cancels out. And even if we weren't working mod 2, we're still going to cancel out the TU, although this algorithm really works with the mod 2 coefficients. So with the mod 2 coefficients, we cancel out the TU. And now my choices for the boundary are ST, SU, TW, and UW. And I want to take the youngest of each of these. So as I go back, I can now go back one more time. So we went back here. We now get UW. Oh, but UW, it's the youngest one, and it is in this list, but I don't want to do that. So now I will add this thing to it. And so now when I add this edge, I will be now adding this triangle. And so when I add this triangle right here, we now have that the UW cancels out. And we also have SU cancels out. So if I now add this triangle here as well, we're left with the edges ST, SW, and TW. In other words, we're now left with this triangle right here instead. So that's now the boundary that we're taking care of. So we now go backwards, but now we're looking only for the edges ST, TW, and SW. So we're going to use that cycle instead to cancel out. SU is not part of that, but TW is. And so we now have STU gets paired with 15. And we could write out all the ones that are positive that are associated with that. I'm only supposed to have written up the positive ones, so the SW actually we didn't need to write that down because anything that's negative, SW is negative. We weren't going to pair it with that anyway. So we actually didn't need the SW either. We only needed the positive ones. And our ST I think is also negative as well, so we also didn't need that one, which leaves us with only TW. And then our last one is SUV. We get the same sort of thing, that this thing now gets paired with 16, and they all get paired up. You can check that out. But that's basically the algorithm in terms of the pairing. So let's take a look at that. Well, let's actually take a look in terms of our pairing here. We can now see in terms of our pairing, we can see how 15 is paired with 7, 16 is paired with 10, etc. in terms of the pairing. What we're interested in calculating is this homology right here. But we also would like the barcodes. Now that we have all this pairing, we can do the barcodes. I can have that 0 started off, and we've got my nice barcode here. I've got 1 was paired with 3. And so all my light colored triangles, they correspond to my 0th homology. And so I've got 2 paired with 9. And so I've got something going from 2 all the way out to 9. So we can use those triangles nicely to get all of these things. 4 with 8 gives us this thing. 5 with 6. That gets us all our 0-dimensional homology. Now let me change my pen color again to now do my 1-dimensional homology. TW was paired with 15, and so we had that triangle right here, etc. We can very quickly get our barcodes that way. So the barcodes, it helps to see what persists and what doesn't persist. So what persists and what doesn't persist. So this one does last for a while, but this one doesn't. And we can also calculate this one. Remember, that is if I go back and take a look at this. We're taking a look at, for example, our, maybe I look at my Z naught at index 0, and then I might mod out by, if P is 2, I'll add 2 to that, and so I might look at the persistence there. So if we now take a look at that, we can also take a look and see if I want to know H0 of 1, 9, well, then I want to take a look at what was created by time 1. And if it's 1, 9, I want to know what exists 9 units later. And 9 plus 1 is 10. 9 units later, the only thing that still exists is my S. And so we know H0 of 1, 9 would be just Z mod 2, because we would just have this one thing generated by S. So you can see that with our various barcodes, there are other ways of visualizing these things. I might want to visualize, note we have 3 variables here, K, I, and P. And so we might want to see, we're actually going to just take a look at fixing K. So we will actually fix K. So fix K. In this case, we'll take K equal to 0. And then we will see how the Betty knot changes as we change I and P. So if I've got my index starts off at 0, my index starts off at 0, then I just have one object. And so we've got this one object for all our persistences because that object actually persists. So we can see this bar right here sort of corresponds to this bar right there. And then if we go to index 1, we now have 2 objects. So we've got these 2 objects right here at index 1. But does it persist? Well, it persists for one step, so it does persist here. But then you can see we go down because we kill it at step 3, so it doesn't persist for that long, and so then it goes away. And so you can also create these, if I fill this in, we kind of create a surface here, or just, this 3-dimensional thing, where we can also visualize it. And remember, the visualization can be helpful. So if we want to compare, for example, autism spectrum disorder to our pediatric control, to our ADHD, maybe this type of graph would also be useful. There is one additional visualization thing which I'm going to skip so that we have a chance of getting further into the matrix method, which we will focus on, but I will ask a question. What does this point here mean? And what does this point here mean? And can you relate it to the number of triangles it's embedded in, and to this quantity right here, or actually the Beatty knot? If I take a look at the number of Z2 components, can you relate the coordinate to the number of triangles the coordinate lies in to a quantity here? So take a look at that yourself and think about that. That's the last visualization for this. We want to focus, however, on the matrix method, because the matrix method will work for all sorts of coefficients, all sorts of dimensions. So it's a lot more general. And I like matrices. One can do a lot of stuff with matrices. So we will now focus on the matrix method. Well, we know for the matrix method, we come up, our boundary map, the boundary of AB is A and B. So if we do Z mod 2 coefficients, the boundary of AB is A plus B. Possibly next week or the week after, I will very quickly demonstrate, in case we don't want to do Z mod 2 coefficients, I will retype out these examples for doing arbitrary coefficients, and so we can compare it for arbitrary coefficients. But today, we will stick with the Z mod 2 coefficients, so 1 equals to -1, and so we've got this boundary right here. Well, that's fine for homology, but we want persistent homology. So how do I get this matrix right here? How do I get that matrix to give me information about the persistence? Well, the first thing I'm going to do is reorder my vertices. So remember, A was born first, D was born last. Okay, in reality, C and D were born last, but we made an arbitrary choice to put in C before D. So when you put in your simplices into your program, even if you want C and D born at the same time, you will have to make a choice, and the order in which you type it in makes C older than D. So we're not going to be using these 0, 1, 2, 3s very much, except for in terms of ordering. And so D being the youngest, I'm going to put the youngest here, the oldest here, and so we will go from youngest to oldest in terms of our rows. However, AB was born before AC, so AC was the youngest, and this one was the oldest. So for our columns, we're going to go from oldest to youngest. You know, it's fair to, those who are born oldest and youngest, to reverse the direction. It will also make sense, because what we're now going to do, let's see, do I have that in? Not yet, good. What we're now going to do is denote this P. So we want to somehow indicate this P in our matrix. Well, I've got that AB was entered in time 1, so now I'm going to use the real time. So we're actually finished with this. We don't need that anymore. That was just to order our simplices, and we didn't even really need it now. We just needed to put it in so the computer program would order these things somehow. Now I'm just going to use that my AB entered in at time 1, my A, though, entered in at time 0, and my B entered in at time 0. So I need to denote that difference. So the P is the difference between we entered in at time I, but we're modding out at time I plus P. And so to denote that we mod out 1 unit later, instead of doing 1, I'm going to multiply by T. So we're going to use T, actually powers of T, to denote the time passing. So we'll put T to say that AB came in 1 unit later, and so the difference between this time and these 2 times being 1, we do T to the 1. For our BC, BC came in at time 1, but B came in at time 0, so sometimes I will go ahead and put these things as the superscripts just to remind me when they entered in. BC came in at time 1. If I do 1 minus 0, I'm going to get T to the 1 again. But if I do 1 minus 1, so C came in at time 1, 1 minus 1, they're the same time, so I could do T to the 0, but T to the 0 is just 1, so I don't need any T whatsoever. So our first 2 columns therefore become 0, 0, TT, and then 0, 1, T0. With my CD, that entered in at time 2, and so now I'm doing 2 minus 1 gives me a T to the 1. 2 minus 1 gives me a T to the 1, and so we have that. AD also entered in at time 2. So for my D, it's 2 minus 1 gives me my T. But now I've got 2 minus 0. A came in at time 0. So now I have my first T squared. So I now have a T squared right here. For my AC, AC came in at time 3. So that came in at time 3. My C came in at time 1. 3 minus 1 is 2, so I've got T squared. And then 3 minus 0 is 3, so down here I've got T cubed. So we get to use the T's to denote when things enter relative to the preceding time. So the time difference, we're looking, the power of the T is really this P right here, the difference between when it enters and when it gets killed off. Okay. So now in better handwriting, we now have this matrix. Now that we've got this matrix, we can do our standard column operations. Remember, we prefer column operations when we calculated the homology of this thing right here. We're going to prefer column operations here as well. Now it makes sense when you think about our row and column operations to do our youngest to oldest, because now I have a lower power. So if I use this row to get rid of this t, I don't have to do any division. I'm not allowed to do division. We can only, subtract off powers. Well, actually, you don't know this yet because we haven't described that yet. We will get into the group theory notation, but probably not until Monday. Actually the module notation, but we'll get into that on Monday. So we don't want to do division, so it's nice to have the higher powers below as well as the higher powers to the right, so that when we do the column operations, that'll be good. And so that's why we did youngest to oldest, oldest to youngest, so we have increasing powers of t as we move left to right, and increasing powers of t as we move top to bottom. Okay. So now we just need to do row operations. But first off, let's go ahead and say a little bit more where these things came from. So I left out some notation. The notation is now we actually, so before we just had, for example, the vertex A. And all I could do was either multiply A by 0 or 1 because we were doing these coefficients, in Z mod 2. Well, now I can multiply by powers of t if I want to. And so we're going to do a similar sort of thing where now we're going to have sort of a double grading. And so we're going to want to know the degree of things as well. And so the degree of just a simplex is just going to be the time when it enters in. So when we had our different times, so we had our grading with respect to our dimension. Now we're going to have a different grading with respect to degree. And so with respect to degree, the degree of sigma I is just going to be the time when it enters in. So A and B both enter in at time 0, so the degree of A and B will be 0. A, B, and C enter in at time 1, so their degree will be 1. Degree 2 is here, degree 3 there, etc. But I also need to know the degree of t squared times A, because I want to be able to move things into the higher degrees, into the later time. So I want to be able to distinguish between being at time 0 and the fact that this thing is at time 2. And I can do that by multiplying by multiples of t. So we will talk about, the degree of t to the n sigma I will just be the degree of sigma I plus the degree of t, which is n. So we just add those degrees. So, for example, if I take a look at this thing right here, I started off with A, but I moved it 3 units over. So now I've got this A is actually t cubed A. So let me actually move the t cubed up here. So this A will actually be t cubed A instead of A. That way we know when we're talking about A being in at time 0 versus A being in at time 1, then we'll do t times A versus time 2 versus time 3. So we do a t cubed A. We know that we're talking about the vertex A when we're at time 3. T squared C, so C came in at time 1. So if I move it over 1, then I would have my TC. If I move it over 2, then I've got my T squared C. And then my AC actually entered in. My AC entered in at time 3, and so this would just be the edge AC with nothing in front of it. So what we have here is this thing tells us that this is an element in at time 3. So we call that a homogeneous element if all the terms are the same degree. So the same degree means that they're all existing at exactly the same time. So we now have that they all exist at the same time. Any questions up through here? So that's just helpful. So now on this chart, we can again say I've got my A. It's in the zero-dimensional homology. I can move it up to talk about TA or T squared A. At time 0, I don't have anything that's one-dimensional, so C1. At time 0, so C1. At time 0 is going to be 0. Same thing, C2, I don't have anything two-dimensional here, so this thing will also be 0 right here. So my C0, it is generated. C sub 0 at time 0 is generated by both A and B, and so we know what our zero-dimensional chains, our one-dimensional chains, and our two-dimensional chains are at time 0, and we can also see that pictorially. If I now want to talk about time 1, well, at time 1, I now have all my vertices, but my vertices would be C and D as well as TA and TB. And then I'd also have my edges AB as well as my edge BC. So I would have all of that. And so I can talk about what my C0 is. My C0 would be generated by, to get A, I have to move it up, so we multiply by T. To get B, I have to move it up, so we multiply by T. C and D, however, have just entered in, so we don't have to multiply by anything at all. And so that's our C0 at time 1. Our C1 at time 1, we just throw in the two edges, the AB and CB, and so we can see, you can figure out what the rest of these things should look like. Any questions there? So now we can kind of see what these column operations would be doing on these things. We have, you can think about in terms of your generators and relators. I can think about these as my generators for my H0, and these as my relators for my H0, or I can think about these things as my generators for H1. So we will look at both of those cases. Right now we just want to do column operations to simplify this. We start off, generally speaking, our E sub i's are just going to be our k-dimensional simplices, but we could talk in more generality as long as it's any homogeneous basis. And we are going to be changing our basis. We just would like to stick with homogeneous, because if I want to cancel out at time p, I want to be in the same time for everything. I want to be in time I plus p. So if we want to cancel out, if we want to cancel out at time I plus p units later, I want everything to be at time I plus p, and so we want a homogeneous basis where everything is at time I plus p. We're going to start off with our homogeneous basis just being our k-simplices. And then we will use the hat notation for the going down one dimension. So if I want to go down one dimension, we'll put the hat on it. You'll notice that for my matrix, the degree of, T, so this was T to my degree business right here, degree of my degree. So this thing right here, it was, remember, just the difference of the 2 degrees. So now the formal way of saying this is that it's going to be the difference of these 2 degrees. Let's go ahead and take a look at that. So I can see that the degree of M row 2, column 3, so M sub 2, 3, the degree is 1. and that is the difference between this basis element and this basis element. So C started off at time 1, C to the D came in at time 2. C to the D came in at time 2. So the degree of this thing is just the difference between the two degrees. So AC came in at time 3, 3 minus 1 gives me 2, and so that gives me the degree. So that is the formal definition of how you choose the power of T. It's exactly what we described before. I've just written it down, and it will hold more general once we do column operations and start changing our basis. So let's start doing column operations. So the first thing we do is we want to do column operations. So I'm going to take a look at for my first non-zero entry. That's CD. So I will switch these two columns. And so now we have these two columns switched here, and we've done our first column operation. Now that I have something non-zero here, I can use this non-zero thing to make this entire row 0. So it's the same thing as when you do the row operations. We're just doing the column operations. So we want the leading term to be non-zero, and we want everything to the right of it to be 0. So that means if I add these two columns, so if I add this column here to this column here, then T plus T gives me 2T, which is a nice 0. So we add these two columns, T plus 0 gives you T, etc. But we've also done a change of basis. So now instead of having, AD, I have AD plus CD. So we have our change of basis here, that now if I look at the boundary of AD plus CD, the boundary of AD plus CD is going to be A and C. D got set to 0. So now our new boundary, remember, we want this column to represent the boundary of whatever generator we're taking here. And that boundary will be AC. And notice that our difference here, our C came in at 1, our A came in at 0. This thing was the sum of two things that came in at 2. And so this was 2 to, so we want this, so we now have T and T squared here, our 2 minus 1, our 2 minus 0, and that just comes from doing our column operations. Those differences will always be preserved when we're doing column operations, so we don't have to worry about calculating these things. It just comes from doing T plus 0, 0 plus T squared. It's all good. So any questions up through here? So we've done two column operations. Let's start off with this one and do another column operation. So now I have my leading entry and zeros here. When I go down here, this is now my next leading entry. I need zeros there. So we go ahead and add now, take this column here and add T times that column in order to get rid of this T right here. So I'll do T plus 1 times T, 0 plus T times T squared plus 0 times T, and that gives me this new column here as well. And notice I still have something homogeneous. I should have done the subscript thing here, but we now still have AD and CD. We're at time 2. BC was at time 1, but I moved it into time 2 by multiplying by T. And so now my differences of these things being time 0, it's still the T squared would still make good sense. And so now I have a change of basis for this column here, and that's my new homogeneous generator. And we do the same thing to remove this T squared. We do the BC plus AC plus T squared times BC, and we get this new generator, and its boundary, keeping track of time, will be this right here. Any questions? So now we'll take this matrix and continue simplifying. And so we now have our, sorry, have to choose the pen each time. So we now have our leading entry zeros, leading entry zeros, or pivots. So I'll sometimes use pivot column as well. So our pivots right here are zeros. This will be our next pivot, and so we're going to want to get zeros here as well, over there. So we will go ahead and take this column, multiply it by t times our AB, t times our AB. That zeroes out these two terms. And then we'll take this column right here. We have t cubed divided by t. We need to multiply by t squared. We can multiply. We're not allowed to divide, but t to get to t cubed is t squared. And so we get our zeros here as well by adding t squared times that column. And so now we have it in column echelon form, where we've got our nice pivots, and we can actually see our homology. So we're now actually ready to calculate some of our terms. We can calculate our B0. Our B0 is the image of boundary 1. Well, these two have image 0. That means they're going to go into the kernel. The kernel's the quickest thing to calculate, so I guess we'll do the kernel first. The kernel is what gets sent to 0. Well, these are the things that get sent to 0, so that becomes our kernel. So it's the null space of this thing here. Our column space is generated by this, but we want to take the image of this. The image of CD will be T times D plus T times C. So we want to note that, notice we keep the T here, because it tells me that we don't cancel out C and D right away. We cancel it out 1 unit later. The image of our BC is C plus TB, so we've got TB plus C. The image of AB is TA plus TB, and so we've got TA plus TB. And so that's the image of our boundary 1 that we can read off nicely from this map here. Any questions there? Okay. So now we can do our H0. We got our column space, so this was our column space from the preceding page. Well, our null space, we don't even need a matrix for that, because we know that everything got mapped to 0. Every single last vertex is a generator, and so all of these things are generators. And so we can now calculate our various different persistent homologies. It would have helped had I put my subscripts to remember when they enter, but fortunately I still remember. Notice that this thing over here, our relators are nice and homogeneous. C and D came in at time 1. We multiplied by T, so now this is degree 2. B and T, B was time 0, T was time 1, and so this entire thing is time 1 right here. TA and TB, 0 and 0 was when A and B came, multiplied by 1, it's 1. So each relator individually is a homogeneous element, but we can see from the picture that we cancel things out at different times. So we will cancel out A and B, B 1 unit later, we'll cancel out C 1 unit later, and we'll cancel out, these C and D 2 units later. So we can now calculate, just based upon our nice group presentation right here, module presentation. I'll get into the algebra later on. I figure seeing an example is good before we get into all the notation. So we'll talk about the real notation next week. But for this week, we can see what our zeroth homology is. Starting at time 0 and 0 units later. So we're just taking a look at the C00, where we have our A and B. We have these two things here. Those are the only things that exist at time 0. And it's 0 units later, so we don't mod out by any, we don't have anything else there. Nothing has to do with 0, so we don't have to worry about that. For P greater than 0, notice we start modding out by things. So if I now do P units later, I still have A and B, but 1 unit later, I've now modded out by this. So now that I've modded out by this, I can get rid of my B, and I'm just left with 1 component of Z mod 2. And since I only had A and B, I can't use C to get rid of B or B to get rid of C because I don't have C. So we just have that for everything else, our H0, if we started off at time 0, then P units later, we will have 1 copy, just A being left, and that is all we'll have. We can see that via the picture. We can see that at time 0, we have exactly 2 copies. If I'm restricting to only having AB, so if I'm restricting to only having AB and that's it, we can see that for all the remaining times we only have 1 component, so we just have 1 copy of Z mod 2. We can also do this for the other cases as well. Suppose now I start off at time 1. If I'm now at time 1, now I have all A, B, C, and D. So now I have all these generators. At time 1, I also have these 2 relators. And now that I have C, now this relator is actually useful. I can use this relator to cancel out B, and I can use this relator to cancel out C. And so we do have that in the first case, we have 2 copies, so we have 2 components right here. But this one doesn't occur until we are 1 unit later. So when we're 1 unit later, then we start getting in these 2 edges. Then we start getting in these 2 edges. And so we now have the additional relator comes into play, and so we go back to having only 1 component again. We can continue doing these things, but I had hoped to go ahead and, oh, we do need to do the barcode, so let's do the barcode. So in my barcode, I can now use this along with the 0, 0, 1, 1 to do my barcode. I know that A enters in at time 0 and B enters in at time 0. I know that at time 1, C enters in and D enters in. I know that at time 1, I kill off the youngest, so I will kill off B. So at time 1, we'll kill off B. A never gets killed off. That was supposed to be a straight line. Obviously, yeah, that was supposed to be a straight line. We'll see what that looks like. C and D, well, we get that C gets killed off right away. This is also at time 1, remember, the degree was 1, so it gets killed off right away. D, however, does last a little bit longer. D lasts only 1 unit longer, though, so we get D gets killed off in the next unit. And so we can draw our barcode this way. And did I have the barcode? No, I did not have the barcode nicely. I'll get the barcode nicely drawn next time so that it's nicely drawn. I'll do that before I post these lectures. We'll continue with this next time. I will post more of this stuff if you want to take a look, but we can also calculate the column space, but we'll have to use the next higher dimensional map as well. So we will do that on Monday, and I'll make sure we'll at least have a few minutes for JavaPlex, but probably not very much. We'll do JavaPlex mostly on Wednesday, but we will start JavaPlex on Monday. Any questions? See you on Monday.